Whatever the true interpretation of quantum theory is, we do know that wave-particle duality seems to be a real thing in the universe, and it has effects that we can observe and measure. One of these effects that will be important in a later lesson is what's called quantum tunneling. What happens in quantum tunneling is that subatomic particles like electrons or protons can actually behave in ways and go places that they wouldn't be able to go if they were particles or only particles. And the way we explain that is that they can get to where they're going as waves and then collapse there as particles. So to give you a little analogy, imagine that our particle is like water. The water can exist as an ice cube, and that would be our electron as a particle in one location. Now, if as a particle, as an ice cube, you try to get this ice cube, this water, over to the other side of this barrier, it wouldn't go. This ice cube simply does not fit under the barrier and can't go through it. But if water is also liquid, then it can flow underneath the barrier. This would be the electron as the delocalized waveform. And then on the other side, it can collapse back into the ice cube and it will appear on the other side. And if we didn't know that water can also exist as a liquid and we couldn't see it, then we go, wow, that ice cube disappeared on one side of a barrier and reappeared on the other side. This quantum tunneling effect is real. I'll give you one example of it, and that is radioactivity. In radioactivity, particles are ejected from the nucleus, from an unstable nucleus, and they carry away a lot of energy from that nucleus. Now, radioactivity is observed and it's measured, but it cannot be explained without quantum tunneling that comes from this idea of wave-particle duality. And that's because remember that there is the nuclear strong force that holds particles into the nucleus, and it's very, very, very strong. It actually sets up what we can call a strong force barrier around the nucleus, and this is the distance that a particle has to get before the weak force stops holding it in place. So to escape from the nucleus in radioactivity, a particle has to move beyond this strong force barrier. But when we do the measurements of a particle, say an electron in beta radiation, coming out of the nucleus, as a particle, that electron should never be able to escape from the nucleus. It should never be able to cross this strong force barrier. And yet, it does because we observe beta radiation. How can we explain that? Well, we can explain that if we think of the electron as a waveform, because notice with this waveform, most of it is inside the strong force barrier, but a little bit of it exists beyond the strong force barrier. So in most instances, statistically speaking, the probability is that most electrons will collapse as particles within the strong force barrier and thus be pulled back into the nucleus. But a small number of them, in fact, exactly the number that we observe in studying beta radiation, will actually collapse beyond the strong force barrier and then will be able to escape and will be observed as a radioactive particle, a radioactive ejected particle. So this is an example of quantum tunneling, that the idea is that the particle cannot cross the strong force barrier, and yet it does cross the strong force barrier. It tunnels through it. Why can it tunnel through it? Because it exists in a quantum state as a wave form that is delocalized enough that part of it is actually already outside the strong force barrier.